While folks are joining in, we'll give people another minute or so before we get started, but we really appreciate your time with us today and during the upcoming holidays. I'm sure that it's a busy time for you and your family, but we appreciate you listening in to today's excellent webinar to end the year. So just give us another minute or so and we'll go ahead and get started. While we're waiting, I just want to thank those of you who were able to participate with us in Providence, Rhode Island last month for our IWCS Cable and Connectivity Industry Forum. It was an excellent conference with folks from all around the world, great technical content, our plenary keynote and various different panel sessions were just excellent. So I'm sure you'll read about those and we'll inspire you to come to our conference again next year in 2025 in Pittsburgh. So let's go ahead and get started. And again, welcome from wherever you are. I see from the attendee list, we've got folks that are late into the evening. So thank you and good morning, good afternoon, and good evening to everyone. My name is Dave Cadu, and I'm the CEO and Director of IWCS, and I'll be your host today. A few housekeeping items. As an attendee, you're part of a larger audience. And so with that, all participants will remain in listen-only mode. And as a reminder, this event is being recorded for rebroadcast and will be available on our YouTube channel as well as linked from our IWCS website. We encourage you to submit written questions during the presentation and use the chat panel that you have. And when you click on that, it'll be on the right of your screen, I think. And after typing in your questions at the bottom, please hit the send button and your questions will be addressed time permitting at the end of the presentation. So today we are honored to have John Ballato, who is a professor of materials science and engineering at Clemson University in South Carolina, USA. John will be presenting his paper on novel optical fibers for sensor and laser systems. John is a professor of materials and science and engineering at Clemson, where he also holds the J.E. Sirrine Endowed Chair of Optical Fiber. So we really appreciate John being with us. And again, hopefully, it looks like everything's set up. So John, take it away. Thank you.
All right. Thank you, Dave. And thank you again for the invitation. Let me add to Dave's welcome my own. It's morning here, at least for the time being, but somewhere in the audience, it's morning, afternoon, evening. So we appreciate you taking this time to spend it with us. So this is, I suppose, an encore of a presentation that was given at the IWCS meeting in Providence a few months ago. And the thought was to try to bring it to a broader audience. So what we're going to talk about for at least the next little while are some novel fibers and their use in sensors and laser systems. But the laser and sensor part is really just to give you some sense of applications. What I really would like to make you think about is that the fibers today are primarily, and I think to many of you, what you can buy off the shelf. And if I'm successful at all in this presentation, it is to convince you that there is a tremendous amount of new and exciting work that is being done and can be done to bring novel fibers, particularly in tailoring their performance at a material level, to do things that you probably don't think fibers can do. And if anything, that's kind of the point of this. you have in your mind, based on the experiences that you have in the commercial and the fibers that you buy or use, that the optical fibers today can only do certain things. And I'm here to tell you that that is a very limiting belief. And I cherry-picked examples to show you a wide range of things that, again, fibers can do or can be used to do if you think differently about the materials from which they are made. Pete Dragic is a co-author. He's my partner in crime from the University of Illinois. My group at Clemson makes all of these fibers. We are material scientists, glass scientists who make fibers, have draw tower and MCVD lathe. Pete does a lot of the measurements and the application side. All right, let's get into this. Let's see, next slide. Okay. Just again, very briefly, particularly as relates to sensors, right? You have light going down a fiber, the sensor is in some sort of, the fiber-based sensor is in some sort of environment, right? It could be in a building, under a road, whatever the case may be. And changes in usually temperature and pressure that act on the fiber are used to change the way the fiber is interacting with the light propagating through it. And it is that change in the external environment that we use, in whatever the sensor is trying to do. When you begin to think about what is it that changes or potentially changes when a fiber is, again, in an environment under stress or temperature, something along those lines, what are the factors that come into play, right? And you see a list of those below. We don't have to go into those in great detail, but things like strain optics. So that's the coupling between strain, so stress and strain, mechanical, and optical, right? So changes in index with pressure or tension. Go 2 down, thermoptic, right? That's kind of the temperature equivalent or analog to strain optics. So you have a change in the refractive index when the temperature is changed. Thermal expansion is a mixed effect where you have changes in mechanical properties like stress and strain, early strain, when you have temperature excursions. Okay, and all of these things are brought to bear on the light propagating in the fiber through the material from which the fiber is made. Okay, acoustic velocity is another one. Usually, in the sensor world, you try to design and develop a fiber that is more sensitive, has an enhanced sensitivity to strain or to temperature. That's not always beneficial, but that's usually the direction you're trying to take these things. Okay. So when you start to think about, okay, I got a fiber, I got light going down it, my environment is changing temperature or it's changing stress, and therefore there is a strain acting on the fiber, which could either be, isostatic, or it could all be in one location, it could be distributed along the length, whatever the case may be. People like me, material scientists, glass scientists who are trained to look at the periodic table, to understand the physics, and then to build a fiber to do what it is that the applications folks need it to do. What we end up having to think about is, okay, light's propagating down, temperature, stress, whatever, changing. What actually is happening? How is it that the application of temperature, the application of stress, which results in a strain, what does that do to the light, to the optical mode propagating in the fiber? So again, the physics of those interactions are known. What the next couple of slides talk about is where does the chemistry, where does the periodic table fit into that physics? And so what we begin to think about is, okay, we take a phenomenon. It could be Rayleigh scattering, right? Because a lot of fiber sensors look at changes in Rayleigh scattering because we can look at that in a distributed fashion. Sometimes it's Brillouin scattering, right? But there's usually some sort of scattering type of mechanism that we use that has a dependence on temperature or pressure. So we then take that Rayleigh scattering or Brillouin scattering, whatever it may be, and we pick out of it those parts that are material specific or material compositionally dependent. So if you look at Brillouin scattering, which is the under one there, the red thing, the strength of the spontaneous Brillouin scattering depends on N, the refractive index, P, which is the photoelasticity. K is a compressibility, which again kind of makes intuitive sense. And we say, okay, well now our job is to apply the periodic table to the making of a fiber. And we know compositionally how to affect the index up or down, how to affect the photoelasticity up or down, how to affect the compressibility up or down. So we can materially control, tailor up and down what that Brillouin looks like. Now, each of those factors has a temperature component contribution and a stress strain contribution, right? So those are the things that we're beginning to get to. But what you'll notice, don't worry about so much Raman, don't worry about the mode instability or nonlinear. That's more for the laser piece of this. But the point of all this is, whatever the physical mechanism by which you are using the fiber to sense, the coupling between that external environment and the optical properties that whose changes in which you are measuring, the coupling between external and internal is material. And we're the ones who understand what it is or how it is that the periodic table imposes those connections. So in the middle, column 2 there, if you will, those are all the different material factors that come into play if you think about Brillouin or Raman or lasers or nonlinear optics and stuff like that. And you say, oh man, that's a lot. There's like 15 things in that table. How on earth am I going to understand each one? And if I tweak the composition, which goes up, which goes down, all that. Well, that's where you get to column 3. It turns out that, again, you may have 15 things, but in reality, there are only 4 or 5. They're really only 4 or 5 things, either directly, like the index, or temperature, or derivative properties like the change in temperature, the change in index with temperature, change in index with pressure, right? We lump that under index. There are only 3 or 4 things that really influence just about everything. And if you know how to turn those knobs, or if you know what knobs turn with what compositional modifications, you can impact a wide range of sensor behaviors, laser behaviors, telecom behaviors, you name it. But you have to understand the material science that is enabling of the light matter interactions that are always what we deal with when it comes to, again, sensors, lasers, amplifiers, telecom. I don't care what your field is, what your space is, your applications are. It is always an interaction inside of a fiber of the light with the material comprising the core, and how is that coupled to the outside environment. Okay, so we think about all of this as a unified materials approach to fiber. Okay, so we have spent, and again, you're going to see a lot of tables and stuff like this, and there's a lot of numbers, and the purpose of them is hopefully not to confuse, but simply to show you that we've spent the last 15, 20 years kind of teasing these pieces out. So the table there is for various things, whether it's density, Brillouin, line width, acoustic line width, photoelasticities, that depending upon what you add to the core of the fiber, you can drive, again, the various acoustic or optical properties up and down, right? And that's really what we're beginning to talk about. And Pete has developed various additivity relationships that say, okay, if you start with silicon, you add this thing from the periodic table into it, then how much should each of these various properties, change in this with temperature, change in this with pressure, or whatever, how do those change? So we can begin to predict for a given application what you need, what is needed. Then people like me in my lab, my students actually, I get to give the talks. They're the ones who have to do all the work. What can we actually make that into a usable fiber? All right, so now I highlight in this table on the kind of the bottom row, you see the kind of the black font and then the bold-faced green font. What's interesting there is under certain or in certain compositional families, some of the properties are positive, some of the properties are negative. And you're saying, well, that's interesting. Where that really becomes interesting is if you mix, I mean, think about this. If you have a material whose, coefficient for a given property is positive, and you add into it a material or a component whose contribution to that same property is negative, you potentially, at the right ratio, can zero it out. Right? So I got a positive, got a negative at a certain ratio of those two, I zero something out. This is one of those places where Mother Nature actually works with us. Very, very few of those, but this is one of them. If you want to cancel out a temperature dependence or cancel out a pressure dependence, this is how you do it. You mix a positive with a negative, you pull that into a fiber if such a thing is possible, and you get for certain compositions a zero effect. Okay, and I'm going to show you some examples of that. But again, this is just to kind of make a little bit lighthearted what we do. This is what a lot of people think, right? The periodic table, right? It's made up of all these things. When I go out and I talk to the optics and laser people, right? There's only one thing on the periodic table, and it's called glass. All glass is the same. Fiber is made of glass. All fibers are fibers. I can't change them. What I buy off the shelf is what I get, and that is absolutely not true. Okay, so I'm going to give you 3 examples of things that you thought fibers could never do unless you think of them through this lens of the periodic table, plus the physics, plus innovative ways to make, not just innovative, but commercially practical ways of making fibers. All right, so let's start with a Brillouin. So Brillouin scattering, a Brillouin athermal fiber for sensing. So this is where we begin to use those positive and negatives effects, right? So you have TOC is thermoptic, SOC is strain optic, and then you have the strain optic, thermoptic, strain acoustic, thermoacoustic properties. And again, with certain dopants like alumina or baria, you see there when you mix them into silica, when you have an aluminosilicate or a barium or bariosilicate, you can offset these positives and negatives. And you see on the right, so again, the thermal coefficient, the temperature coefficient of Brillouin versus the strain coefficient of Brillouin. As you add, say, barium oxide into those silica fibers, you get these significant reductions in that coupling, in that coefficient. And at certain compositions, they go to 0. We've not quite gotten there in the barium oxide dopant, but we have in the alumina dopant. So if you make a aluminosilicate fiber with high enough alumina concentration, which we have done in the bottom there, you have a fiber whose Brillouin response is temperature independent. It's athermal. That means that makes it, or its temperature behavior is 0. That makes it only strain sensitive. So normally in sensors, you have temperature and strain, and you have contributions from both of those things. So if you have a sensor and you say, well, I don't know if that is because of the change is because of temperature or because of strain, the way that is deconvolved is through the electronics, or you have to have a sensor system that has multiple fibers, each with a different temperature and strain dependence. And then you have all the complicated electronics and circuits to then deduce, okay, well, what is the strain? What is the temperature? We have a fiber here that is only strain dependent. The temperature dependence goes away because it's temperature athermal in its Brillouin response. So the fiber is doing the work of the complicated, expensive, system complex electronics. And if you want to take away from this, let the material science, let the material and the glass do the work for you, rather than the electronics do it for you. That makes your system simpler and it makes it cheaper. Okay. So the fiber is doing the work for you because we understand how to make the glass do that special interaction with the light. So this is one example. It's not the only example. So this is a slightly more complicated one, but again, it works. All of these are done in silica. All of these are done using commercially scalable methods. So this is a lithium aluminosilicate. This is a little bit, as I said, different, where you're playing with the acoustic velocities and the temperature dependence of the acoustic velocities, and the fact that silica is somewhat anomalous, so that when you heat it up, certain things go in positive directions, certain things go negative. There's also a fairly large thermal expansion mismatch between the core and the clad, and those work in opposite directions. So in this case, you have a similarly athermal from a Brillouin scattering perspective fiber, but it's single mode, which again, you oftentimes need in many sensor applications, so you don't have modedness coming into the behavior. But this is over a wide temperature range, thermally, or it's a Brillouin athermal. So all that you see are strain effects. And there are other versions where they are atensic, which means that you only see temperature effects because the Brillouin is then insensitive to strain. Okay, second quick example, because I'm going to try to give time for questions. Rayleigh and fiber Bragg grating athermal. So this is a little bit more tricky. So when you start thinking about you have a fiber Bragg grating or you're using Rayleigh scattering in a sensor modality, you have similar types of convolutions with respect to temperature and strain. Okay, and you can think about this with a grating, right? As either you strain the fiber that has a grating in it, or it heats up and you get thermal expansion, and therefore there's a strain associated with temperature through thermal expansion. Then the grating wavelength changes, and there are reasons why you would want that to be a thermal. Well, so in this case, instead of looking at again the Brillouin behaviors, you look at the therm-optic or thermal expansion behaviors for this type of sensor modality. So but following a similar prescription, you can look at silica has a certain therm-optic DNDT, certain therm-optic value, positive. There are dopants into silica, like phosphorus, like boron, so P2O5 or B2O3, that have negative therm-optic behaviors. So as you dope silica with P2O5 or B2O3, the effective therm-optic coefficient decreases. And you see that kind of on the right, both for just a kind of a bulk material versus a core clad fiber structure where you have thermal expansion taking into account. The thing here is that it takes fairly high concentrations of those dopants to get to an athermal condition, much higher than you would normally think to use if you're using those for either telecom or say datacom or laser applications. But that doesn't mean they can't be made or done. They're just additional complexities in the fabrication, but it can be done. And I'll show you that in a moment. But in this case, you're again playing off understanding the chemistry, understanding the periodic table, understanding the physics, and understanding fiber fabrication, fiber formation, and the nuances of the material science during fiber formation. You're playing off positive and negative values. The previous case was Brillouin related, and in this case, it's therm-optic related. And so here's a kind of a representation of that. To first order, you can do this with borea and germania, which again are common dopants that you can use or you do use in many commercial fibers. You see in the graph below, those are actually data points from fibers that we made. At Clemson, the solid diamonds are measured on fibers, directly measured on fibers. When you get to the right at these high concentrations, because the effective boron oxide, B2O3, in silica is to actually reduce its index. It reduces the therm-optic, but it also reduces the index. When you go to too high a concentration, the core has a lower index. The doped core has a lower index than the undoped pure silica cladding, and so it's an anti-guiding fiber. Now, again, there are tricks to deal with that. You add more phosphorus and other things that raise the index. But in our measurements, we hadn't gotten far enough to do that yet. So those are anti-guiding fibers, which is where they're denoted as an open diamond as opposed to a closed diamond, filled diamond. But nonetheless, the point is you can make these fibers. You have the additional considerations with respect to making them index doping. But again, that's where we're going. But we have made fibers that at least compositionally would be in excess of where you have a zero therm-optic effect, and that would give you a athermal fiber Bragg grating structure or sensor structure, lone period grating structure. If you do also have to take into account things like the thermal expansion, which is the alpha in the equations above, if you want to take that into an additional count, then you need a slightly lower effective thermoptic coefficient, which means you'll need more of the dopants. But that becomes very interesting for athermal gyros. So those folks that are interested in gyroscopes that are not temperature dependent, then this is a route to doing that. All right, moving along. Fibers that heat and cool or cool. So this is kind of another strange thing, right? Because, you think of a laser going, lasers, whether it's Star Wars and or Austin Powers or whatever, or in the real laboratory, the real life, you think of lasers as hot, right? And that's because when the laser light hits something, right? Whether you're cutting or welding, whether it's just high power laser light going down a fiber, the light there's some residual absorption, or there's a lot of absorption in the case of cutting and welding. In the case of, just lasers and amplifiers, there's just residual absorption, or could be the cladding, or I'm sorry, the coating. Nonetheless, lasers are thought of as heaters, right? Lasers get hot. Question we were posed is, could you make a laser that cools when it runs? And there are a couple of ways of going about doing that, but let's talk quickly about the how does one do this. So lasers heat because of what's called the quantum defect, right? So there's an energetic penalty. You pump it to a higher energy, there's a relaxation, you get a difference between the pump energy, the emission energy, and that difference goes into heat. That's called the quantum defect. Ytterbium, it's only about 5%. In erbium, it could be as high as 60%. And if you're scaling to, hundreds of watts, if not kilowatts, 5% is still a lot. Now, normally, to cool a fiber, to cool a laser, you have to either use circulating coolants like water or air, or you use thermoelectrics. But nonetheless, you got to get rid of this heat, and that adds to the complexity, it adds to the cost, it adds to the weight, it adds to the size. None of those things are good. So there is physics called anti-Stokes fluorescence, where instead of pumping to a higher excited state and letting it relax and getting heat off, what you do instead, say with ytterbium, is you pump from the bottom of the ground state to the top. From the top of the ground state to the bottom of the excited state. The electrons in those levels have to take on a Boltzmann distribution, so they thermalize to form that desired population. In thermalizing, they suck in that energy from the heat from the material itself, the phonons of the material, which annihilate the electrons, suck in the energy, annihilating the phonons, which is cooling. If that photon is then released and removed from the system, it takes that excess energy with it. And you see that on the right. That is an anti-Stokes fluorescence process, and it leads to cooling. And so what we've been able to do with again, Pete at Illinois and Michel Digonnet at Stanford and our respective students is understand that physical process, understand the material science that enables it, go to high doping concentrations, very, very low loss, very high quenching concentrations, and make a silica fiber fabricated using commercial methods that cools when it lasers, or when it amplifies. Or you can drive it to a thermal where you have fluorescence, which leads to cooling, lasing, which leads to heating, and you offset the cooling, fluorescence, and the heating, lasing to get an athermal, what is called radiation balanced fiber amplifier or fiber laser. Think about a system where the laser, the fiber, is cooling or not at least heating, right? So it gives you another dial to turn in the thermal management, another tool in the toolbox of thermal management for your laser systems, amplifier systems, sensor systems, okay? But again, this requires understanding and appreciation for the glass science, for the fiber formation, and understanding the physics. Can you work it the other way? Can you make a fiber that is so heavily doped that all the light is quenched and converted into heat? And the answer to that is yes, okay? So we've done this as well. We've put so much dopant into a fiber that all of the pump light is absorbed within about a millimeter, 1 to 2 millimeters of the length of fiber. And you see that on the right. So these are about 15-20% ytterbium concentrations in the fiber. You see on the bottom, it gets up to hundreds of Kelvin temperature changes in virtually no time, because that absorption and non-radiative relaxation that gives you heat is virtually instantaneous. It's morning here. It's kind of gross, but that picture on the bottom is a piece of chicken where you can go in. Think about doing this inside the body, where you can do cauterization with something that is the size of your hair, right, of fiber, and only a millimeter or two fused onto the end of a transmission fiber can do cutting, can do cauterization, can do heating inside. So again, we're understanding the chemistry, understanding the physics, understanding fiber fabrication, and the nuances of those things. We can now make fibers that are heaters, amazingly efficient heaters. We can make them cool, or we can make them athermal with respect to temperature, with respect to pressure. We can apply those to laser systems, amplifier systems, telecom systems, and sensor systems. Okay, I need to move on. So all of these fibers are made using one of two methods. MCVD, in the second set of bullets, MCVD is a commercial process. It is an industrial process. It is what all the manufacturers who make laser fibers use. So it's done. For some of them, we use what's called the molten core method. It is more for specialty compositions that you can't hit with CVD methods, but it is still scalable. It uses the exact same type of draw tower you would use for making commercial fibers. So what you use depends on what composition you need. Which method of manufacturing do you use depends on the composition of the fiber that you need, which obviously depends on the application that you're going after. But if there is anything that I hope I showed you, is that not all fibers are the same, that we understand kind of all these gives and takes. The periodic table for fiber is not just silica. It is a much broader cross-section of the periodic table than you would normally think possible, okay? So, right, fiber sensors, which we talked about, and amplifiers and lasers, they look at these external influences on the internal optics, but those are fundamentally light matter interactions. And what we do, and what we hopefully have shown you, is that there's a tremendous amount of tailorability in that matter part, so that you can influence the light matter interactions much, much more significantly, and even negate them and zero them out in some cases. And you can, as I said, make fibers that are either Rayleigh, Brillouin, or just, optically athermal, atensic, or have enhanced or reduced sensitivities, right? And so I kind of always finish with this. Mother Nature always wins. But fundamentally, all these things, as I mentioned, are light matter interaction based. And so the optics and laser people, that's the light piece. Us, right? We're the material science. We're the glass scientists. We're the matter people, right? So everything is light matter interactions. It's time that the optics and laser people start talking to the matter people. And so, as I say at the bottom there, be Fender glass scientist, let nature do the work for you. So with that, I will thank you for your time, and hopefully we have a little bit of time for some questions. Dave, back to you.
Yeah, John, thank you so much. Very intriguing concepts that really, only academia can figure out, and it'll really, transition to something very practical and commercial for the world. So thank you for your efforts, your work, and your continued involvement with your students. This will clearly drive us into the future. A number of intriguing questions. First of all, how are these dopants applied to the glass? Is it in the preform stage? How do you do that?
Right. Thank you. That's a good question. Depends on which of those two methods that you use. Some of the dopant, and it depends, obviously, the application specifies the dopants. Some of the dopants are, again, conventional dopants that are already used in existing off-the-shelf fibers. commercial fibers, we just pushed their concentrations to higher levels that most people would not think to use. So that's one thing. But we build them into the preforms, and then we draw the fibers using, because we have at Clemson the same equipment that the specialty fiber manufacturers have. So that's helpful because we can transition those technologies much faster. In the cases where there are very, very high concentrations, and we use that other method, that molten core method, we build that actually into the preform as well, but it's a little bit simpler approach to building it into the preform than using CVD. But in every single case that we talked about, a conventional draw tower was used, a silica cladding was used. And again, these are things that we've worked on and played with and understand over the last 30 years. So they are scalable. These are not one of the filters my group applies when people come to us with problems like this is if it is not a solution that is commercially scalable, we're not going to try to do it.
Sure. So the applications of this technology, the material science that you're applying here into the fiber is predominantly geared towards sensory, right? Sensing properties, laser properties. And so is a particular dopant, such as alumina, if that's put into the fiber, what's the effect? Do they have a detrimental effect or impact on the data transmission and fiber attenuation?
Right. It depends on what you're trying to do, right? We at least in our thinking, we always start with what the application is, and based on the application, what matters and what doesn't matter. And then based on what matters and what doesn't matter, then we kind of down select what dopants drive or reduce the interactions that we want in a way that doesn't influence or create other problems. And again, we've been working on this long enough that we have a pretty good sense about what to add, what not to, maybe more importantly, what not to add, depending upon what it is that you're trying to do. But every single one of those examples is kind of case specific to the application.
Right. And do you have any thoughts on the viable, distances, the link distances for some of these applications?
Right. Yeah, that's a great point too. Right. So everything we talked about is you would, I think, primarily categorize as specialty, right? So these run from meters, right, all the way to maybe tens or maybe tens of meters, right? This is not, I'm not talking about anything that is like subsea or long haul or, something like that. So these are all tens to hundreds of meters kind of lengths. And over those shorter lengths, the losses are not the requirement on losses are usually not quite as severe as they are for, say, long haul datacom subsea types of fibers. The MCVD ones are going to be on that same kind of datacom level, for a dB per kilometer type of thing. The more specialty, highly doped molten core ones, those will usually be hundreds of dB per kilometer. So a fraction of a dB per meter to maybe a dB per meter. So again, it just depends on what you're trying to do. Some of the laser fibers or the amplifier fibers, those are maybe 10 meters long. So they have a much more, their loss budget can be, not quite as bad. The Brillouin fibers, those again are meters to tens of meters. So you can get away with, some higher level of loss. That does factor in, and that's kind of one of the conversations we end up having with various partners. What is, again, what are those must-have? What are those may-haves? What are those can't-haves? And go from there.
Exactly. Okay. How will the wavelength of your laser source affect the dopant material choices of the fiber?
That also factors into the application and where are we going with this. Mostly, we think about sources at 1 micron, 1.5 microns, and 2 microns, right? Datacom, telecom, any of that stuff. A lot of sensors are at 1.5 microns ish. A lot of laser applications are at 1 micron. we have some people that are interested in 2-micron sources. We have a project on actually visible fiber lasers. Anybody's interested in visible fiber lasers, let us know, because we're looking for friends there. It does factor in, and the material, the things that we talked about. What do you put into the core for a given enhanced or reduced interaction of light with whatever the environment is? That does depend on the wavelength. Sometimes a lot, sometimes not at all, but it factors into one of those sets of conversations about what you're doing, why you're doing it, what you need it to do.
Sure. And is it possible perhaps to build an amplifier, a fiber amplifier for, say, the 400 to 500 nanometer range? Such as gallium nitride,
Yeah.
again, back to the periodic table, I guess.
Yeah, it is. We just started, so give us time. We just started a visible fiber laser fiber amplifier project about 6 months ago. And it's proving to be very, very interesting. So I do actually think that that's possible. We with our partners, so to give them credit as well, we have made some visible fiber lasers using exactly the same types of things that we've talked about here. But that's just a very nascent effort. But it is something that we are interested in. Hence the email addresses in front of you.
No, I'll remind folks of the contact points, because obviously this leads into some good interactions, some good partnerships potentially. How do you isolate the measurements of, say, Rayleigh versus the Brillouin? Is that how you pronounce it?
Yeah.
Yeah.
Right.
Scattering against other types of losses, and can a typical OTDR perform these measurements, or do you need a specialized laser?
OTDRs and things like that are based on Rayleigh, right? So if you're looking at a phenomenon that is Rayleigh related, then OTDR is for you. Brillouin is a little bit different because it's a nonlinear process. So you look at a change or a shift in the frequency from your excitation. But again, for people like Pete, I mean, that's their expertise. They know exactly how to do it. And there are Brillouin-based sensors. Actually, there's an entire community within the fiber sensor world that is Brillouin-based. So those things are known to people in those areas.
Great. How commercially ready or available are some of these technologies that you've been discussing?
I would not say any of them are commercially available in the sense that you can call a company and buy, but as I said, all of these fibers that we reported, well, I'll give you two answers. All of these fibers that we reported were made at Clemson using, as I said, one of two scalable methods of manufacturing. The CVD is a commercial method. Any specialty fiber manufacturer uses the exact same type of equipment we have at Clemson. So that transition path is really quite straightforward. The molten core derived fibers it uses a standard draw tower. We have that know-how that also could be transitioned. The second part of that answer is the reason that I'm thrilled to be giving these types of webinars is because we have made these fibers. We are looking for partners to commercialize them. So, and even if you don't need them necessarily commercialized, we have made these fibers. We have these fibers, and we can certainly work with you on getting access to them.
Yeah, and I think looking at the audience here today, as well as the registrants, and also future publicity, we can hopefully build those relationships and those contacts with some leaders in the industry. So thank you for that. Is the athermal fiber for FBG available now?
Well, it's available in the sense that we've made them, and between
Right.
me and Pete and others, we have them. But we have the recipes. We can continue to make those. Where we're going, maybe that's the way to talk about it. Where we are going with those fibers is in some of those, and it depends on where you are on some of those diagrams. Remember, I mentioned some were anti-guiding. So a lot of our effort over the next year is going to be to continue to reduce or to balance that thermoptic or offset the thermoptic and the thermal expansion contributions to get that to be perfectly athermal, but still index guiding, right? That's the next piece for us, is to take those open diamonds and move them up to be, filled diamonds. We know what to do. We just haven't finished doing that yet.
So any final thoughts on what the next steps are to become commercially available? I mean,
Industrial
obviously it's a technology that might be applied into, fiber manufacturers and things like that.
Yes. Yeah, I think in all of these cases, and again, it's part of our kind of DNA and our philosophy, is that we only really want to be working on fibers that we see a commercial pathway to. What we need is our partners, right? We need fiber fabricators, companies that either on the specialty, primarily I would think on the specialty side, but that are interested in looking at new markets, new products, but understand and have the capabilities to make fiber that we can transition that to, and people to use them in new applications so that we can, there's a market pull. People on the application side to play with them, to show that, that they are as useful as we believe them to be, to create market pull so that, the fabricators out there will see that there's a market for them to get into this.
Great. One final question that I see that's probably the most important is Clemson going to beat Texas this weekend?
Next weekend.
Next weekend.
Okay. I'm gonna get some heat for this, but I don't think Clemson deserves to be where it is, quite honestly, based on its records and who we've lost to, and we have not put together full 4 quarters of championship level football. So if we can actually put together 4 full quarters of football, then I think the answer is yes, we can run with anybody, but we haven't done that yet. So I am not optimistic. But we'll see.
Well, good luck to Clemson. And again, based on your presentation today, there's a lot of good things happening there, if not the football team. So anyway, very much appreciate your time. Again, for those of you who wish to contact John, you can see his email address here. We look forward to our next technical webinar, which is scheduled for January 17th. It's a Friday. Typically, we run these on the 3rd Friday of every month. And each of you will be receiving an announcement for these events. So please feel free to share our announcements with your colleagues so that they can join and register as well. It's important that we take a second here to recognize our appreciation for our partner level sponsors, for IWCS, who contribute greatly to the success of our forum. And without their strong leadership and generosity, we would not be able to bring these important technical innovations and information to you and our global audience. So again, thank you to these leading suppliers in our industry for your support. And I do want to recognize that this was our 100th webinar for IWCS. We started this program 5 or 6 years ago, and it's been really tremendous to bring the very best of our conference presentations to you. And again, it's an honor to have John here for our 100th webinar, which are all available on our website or through our website and on our IWCS YouTube channel. So you can look at the entire index and find those that are of most interest to you. But for over 73 years now, we've been bringing our conference and information and technical innovations to our global community. And our 74th annual conference, which is well underway in terms of preparation and developing the content. It will take place in Pittsburgh, Pennsylvania, on Monday through Thursday, October 27th through 30th. And so as we're evolving our program, and certainly the call for papers for you and your colleagues, if you're doing some really good work, outstanding opportunities for your company to approach our entire technical community, please consider entering an abstract in our call for papers over the coming months. And we look forward to accepting that and have you present in our upcoming conference. So with that, a great way to end the year. I wish you and your family a very healthy and happy holiday season and a fantastic new year, and look forward to being with you again next year. So all the very best to you. Have a great weekend and stay warm. Take care. Thanks, John.
Thank you.